When you take physics 2, you start suffering a lot because it's much harder than physics 1. And I think part of the reason is uh, things in physics 2, they move without touching, right? Nothing is pushing it, but there's something that's pushing it, right? It could be a charged particle in an electric field, or some magnet inside a magnetic field, or it could be a combination of both, right? So there's like a force and magnetic field and electric field. They have to be perpendicular and all that. So uh, when you get to this, to really understand what's going on in physics 2 or electromagnetics, you need to have the concept of vector fields. So what's a vector field? So let's think about something like this. If you have a charged particle and it's being shot at some, it's shot into some space, and there's like some electric voltage going on in there, which would create electric field. So let's think about that. You might have a electric field E that's trying to push it like that. And if the charge is Q, then the force is given by Q times E, right? So these are both vectors, right? This is a vector. Q is a scalar. So you recognize this formula? Mm-hmm. You've seen it a lot of times, right? And what it's going to do is, because it's kind of pushing in a different way, this is going to go bend towards like that, something like that, right? And at the same time, not only it will bend its trajectory because of this electric field, it's probably going to accelerate because there's this component that's already positive here, and this force makes this direction force bigger and bigger as it progresses, right? So you want to be able to describe such a thing. To model such a situation, you need to think of E, vector field E, as something that where if you give a point or the location, then it gives you a vector, which gives you the strength of the electric field at that position, right? In other words, E is a function that would accept two values, x comma y, the position in the space, right? And it's going to give you two numbers back, just like that. If you feed in two values, you're going to have a function that gives you the x component, and you're going to get a function that gives you the y component of the vector. And such an example is a two-dimensional vector field. Now, one of the common things that you want to address is what will be the amount of energy gained by this particle as it goes through this vector field, right? I mean, it's going to speed up, so the kinetic energy will be increasing, right? So how do you find out that quantity? And use the fact that it's really the work done to the particle that is how much the kinetic energy has gained, right? If you do more work, then you can add energy to the moving particle. Does that make sense? Right. And then let's say this particle is moving at a trajectory RT. So RT is the trajectory of this moving particle at time t. Let's say we for some reason we were able to get this thing. Okay, so at each time t, this gives you two coordinates, x and y. So RT looks like xt comma yt, right? So at every moment you know where the particle is, and then you have to compute the work done to the particle, and the total work done to the particle, and we always use the same principle. It's in calculus, the whole is sum of its parts. Oops. Right, just like that. And then, what is work? Work is force times distance, right? Yeah. Force times distance, but that's only when the force and the displacement is exactly in the same direction. If they are different, then instead what do you have to do? Force times distance times cosine theta. Have you seen this formula with the cosine? Yeah. That's when your force is like that, but the distance is like that, and there's an angle theta. In that case, you have to project the force to get only the component that's moving in this direction to figure out the actual work done to the thing. But we know better that now that we know vector calculus, we know that this is just another way to write down the dot product, right? The dot product is norm of the first vector times the norm of the second vector times cosine of the angle between. So you can really say that the work is force as a vector dotted with displacement as a vector. Okay? So that's what we are going to do. And in this format, the displacement is a small change in the position r, right? So the way we are going to do this is we're going to say you need to integrate the force dotted with dr. Okay. And doing this calculation will tell you how much kinetic energy this particle gains. And using that, you can also figure out if, let's say there's an electric field here and then this goes into it and then escapes it later, then you can figure out how much would be the terminal velocity, how fast it's going to go. Yeah. So earlier I was like asking about railguns and stuff like that because like that's an example where a moving particle gains speed because of the force field and exits, and there's a terminal velocity like that. And all of that is related to calculating this integral. All right, so that was like physics talk. I know some of you just get lost if I say that. So if I just go to math, what's the beauty of math? The beauty of math is that you just strip out all of the complicated things and just look at the core, the hardest part, and see what's going on. So we're going to now forget about the charged particles and electric fields and all that, and just say we have the following things that we are interested in. So the first thing is vector field, which is simply a function which accepts two values and gives you two values back. The way I write this is f is a function that takes in two copies of r. So this strange of writing this r, that's a set of real numbers. So if I say r squared like that, that's like pair of real numbers to a pair of real numbers. It accepts two real numbers and it gives you back two real numbers. That's the way people write down that thing. And this is an example of a 2D vector field. And if you have x, y, z, if you accept 3 values, and it gives you back three real values. So all of x, y, z are functions of those 3 values. In this case, you get a function from R3 to R3, and that will be a 3-dimensional vector. Example. F x y equals to y comma negative x. Now, there is a way to figure out what the vector field is doing, which is to just try to draw the vector field at every point. So if you plug in 0, comma 0, you get 0, right? So at the origin, this vector field doesn't do anything. What happens if you're at 1, comma 0? 1, comma 0 means you have 1 for x and 0 for y. So that gives you 0, comma negative 1. 0, comma negative 1 is a vector that's pointing downwards, right? Now, although to do justice, I should really be drawing a length 1 vector. Then if I do that, it kind of overlaps everything. So sometimes you might scale it down by like pointing down, but let's just imagine that it's scaled down so that this is really 1. What if you plug in 0, comma 1? So you're here. Well, 0, comma 1 gives you 1, comma 0, so it gives you this vector, right? Okay, so I'll give you a minute to think about what happens here. Negative 1, comma 0. Which direction will the vector be given? What do you get? At negative 1, comma 0, if that's plugged in, x gives you, x becomes negative 1, y becomes 0, so the output is? Oh. Yeah, it's going up, right? 0, comma positive 1 is what you get, right? So you end up with a vector that's going up. And you can continue doing this like for other points. So you get something like that's like swirling. So this kind of vector field would appear as the velocity field of a fluid that's rotating this way. So if, for example, if you were making cocoa and you poured hot water onto cocoa powder and then you're doing this, right? Then on the surface, the top of the fluid, you're going to see this kind of pattern. Right? In the middle, it'll be kind of short, but it'll be doing this. So that's an example of a vector field. Another example would be, say, f x, y, z, say something like x plus y, y plus 2z, x times y times z. I have no idea what that looks like. But you might be able to use some computer graphics software to show the vector fields for this 3D. But let me just ask, what's the vector you get if you plug in 1, 2, -1? One plus 2, so that's going to be 3, right? Y plus 2, that's going to give you 0. 1 times 2 times -1, that's going to give you -2. Right? Yeah. So that's it. Simply, what's a vector field? A vector field is something that where you plug in a few, like either 2 real numbers or 3 real numbers, and you get back a vector. That's what it is. Now, as I said, one of the key interest for us will be doing something like this. Suppose RT is, say, t comma t squared. So what does this do? It takes one value, it gives you 2 values back, right? So at each time t, it's going to give you a vector, which is a location vector, it's a position vector. That means that every time t, you get a position of a moving particle, so it's a trajectory. Another way to say it is that this is a moving particle. It's a trajectory of a moving particle. That's what it is. And the question here would be, let's say t goes from 0 to 1. Okay. So call this curve, this trajectory, C. And the question is, what is the integral over this trajectory of the following vector field, which is, let's say, x plus y, x minus y, dot dr. Okay. How would you do this? That's the question. So you have a vector field. That's a vector, right? You can do the dot product. And you want to calculate the value of this. And, well, I don't have time to demonstrate how to do this, but there's just one fact that you have to remember. The only thing that you have to remember in order to do these questions is the following trick. You want to divide by dt and multiply by dt. That's it. So that's one thing that you have to remember. Always, when you're asked to do questions like this, just divide by dt and multiply by dt. That's it. And I'll explain what I mean by that next time.